Now let's take a look at basic layer 2 bridging and switching operations. Here we have a switch with 4 devices attached, device A, B, C, and D. For simplification purposes, we're going to summarize the MAC address of each device simply by saying AA, that's the MAC address of A, and BB, C, and D, etc. Here, initially, when the switch is first powered on and devices are first plugged in, the switch's MAC address table is empty. Device A sends out a frame to device C. Here's the source address, destination address. Device A sends a frame to C. The frame comes in on port 1, and the switch looks at the destination address here. The switch compares that destination address to entries in its MAC address table. Since there are no entries here, the switch recognizes this as an unknown or unrecognized destination MAC address. Switches flood all frames to unknown MAC addresses, which means that the switch takes a copy of that frame and floods it out of all ports other than the one that it came in on. In addition to this, the switch learns the MAC address of the source device from the source address field here, associating that address with the port that it came in on. After device C sends a response to device A, now this frame will be compared, the destination field will be compared to the entries in the table. Notice now there's actually an entry for A's MAC address here, and so now the switch knows that it can take this frame and forward this frame out of port 1. At the same time, the switch does something called filtering, which means that the switch is not going to send that frame out of the other ports where you've got device D and where you've got device B. So it will forward it out of port 1, but it will not forward it out of the other ports, of course, nor will it forward it out of port where C is attached to. In addition to that, of course, the switch learns the source address of C and associates that with the port that C is attached to. Eventually, the switch will learn all of the MAC addresses and associate them with the appropriate ports. If either of these devices sends out a broadcast, and I'll just sort of abbreviate that with a bunch of F's, at layer 2 there's a sequence of hexadecimal F's in the destination frame field here for a broadcast address. The switch does the same thing that it did with all of the previous packets. These were unicast packets right here, and this is a broadcast packet. However, the switch still operates the same way. The switch will take this destination field and compare it to the entries in its table. If there is no match in the table, the switch does the same thing that it did before. It does not recognize the destination address, so therefore the switch floods the frame. This is the reason for the behavior behind the way that broadcasts are sent. Switches are considered to have all devices in one broadcast domain because if a broadcast is sent, then that broadcast would be sent to every device on the entire network. This is called being one broadcast domain. The thing to keep in mind here, it's not because it's a broadcast, but because it's an unknown or unrecognized address that the switch is actually doing this behavior. So it's not the behavior that we want to focus on, but it's the actual addressing here that makes this a broadcast. So that's a basic look at layer 2 switching.
A bridge connects two separate media segments that both use the same protocols. It reduces network traffic by intelligently passing signals between the two media segments. In this example, Computer 1 sends a message to Computer 3. The bridge prevents additional network traffic on media segment B by stopping the signal at the bridge. Next, Computer 1 sends a message to Computer 5. This time, the bridge allows the message to pass to media segment B and on to computer 5. In this example, we will examine a bridge that has just been added to connect two network segments. When a frame arrives at the bridge, it looks for the source address in the packet. It then looks for the source address in its table. If it does not find the address in the table, it adds an entry, noting the segment on which the frame was received. It then looks at the destination address in the frame. If the destination address is not in the table, the bridge forwards the frame to all other segments. Now suppose that computer 2 sends a message to computer 1, which is on the same segment. The frame arrives at the bridge, and an entry for computer 2 is added to the table. The bridge looks for the destination address in its table, in this case, computer 1. It finds that the destination address is on the same segment as the source address. In this case, the frame is dropped and is not transmitted to other segments. Now suppose that computer 3 sends a message to computer 1. The bridge records the address and segment of computer 3 and forwards the message to computer 1. Eventually, the bridge will learn where each device is located and forward those packets that need to cross to a different segment. A switch is similar to a bridge, but a switch has multiple ports and can perform switching tasks much faster. When a message arrives at a switch, the switch examines the destination device address. The switch database contains a list of its ports and the devices attached to each port. It locates the device address in its database and forwards the message only to the port where the device is attached. Most switches can simultaneously switch traffic between multiple ports. This allows multiple devices to transmit at the same time.